The next chapter here is talking about the ionic basis of resting membrane potential and the action potential. So I've been alluding to this electrical impulse called the action potential, and the fact that neuronal cells, along with muscle cells, are excitable cells. And we're going to talk about what that really means. So we talked about how there's a different composition of ions and other particles in the intracellular fluid compared to the extracellular fluid. And one of the most important differences between inside and outside of the cell is the composition or the concentrations of sodium versus potassium. So we did talk about how there's a greater concentration of sodium outside the cell and a greater concentration of potassium outside the cell. But additionally, there's also a much greater concentration of amino acids and protein, represented here in this slide by a capital A. Okay, and amino acids and protein that are trapped in the cell that can't get out of the cell have an overwhelmingly negative charge to them. So when we look at the one of the implications for this different composition inside and outside of the cell is that we have lots of charged particles, and they're separated by this membrane, this plasma membrane that doesn't allow them to cross. Okay, so it isolates these different charges across the membrane. So when we look at an average cell, even though we have lots of potassium inside the cell, which is positively charged, the number of amino acids and proteins are so overwhelmingly large that the inside of the cell tends to have a net negative charge, and the outside of the cell tends to have a net positive charge. So we have a term to describe this difference of charge across the membrane. It's called membrane potential. Okay? So a potential is just simply defined as a difference in charge across an area. Okay? A difference in charge across an area. So that's what potential means. So membrane potential is the difference in charge across the plasma membrane. And we express this difference of charge in terms of what we call voltage. So when we talk about membrane potential, we're looking at the charge inside of the cell compared to outside. And we're going to express it in units of voltage called millivolts. Okay? So the average cell has a membrane potential that's going to be negative some number in millivolts. Okay? So we'll talk about what that number is and how it's really created. So the basis for the membrane potential, or the difference in charge across the membrane, is determined by the specific ion composition of intracellular versus extracellular fluid. So let's talk about these ions. We know that there's a greater amount of sodium outside the cell, greater amount of potassium inside the cell, and they have charges to them. Both of those ions are positively charged. So I'll go back to this previous slide. So we talked a lot in the first lecture about diffusion and passive transport. And we talked about how diffusion happens, or passive transport happens, down a concentration gradient. So we talked about concentration gradients, that substances are trying to get from an area of high concentration to low concentration. But what we didn't mention was that when a substance is charged, like sodium, in addition to having a concentration gradient, they will also have an electrical gradient. So ions, charged ions, which is actually all ions are charged, but particles in solution, solutes that are charged, like ions, are going to have both a concentration gradient and an electrical gradient. And while the concentration gradient is directed um, from high to low, an electrical gradient is basically when a charge is attracted to the opposite charge. So um, sodium, for example, is always going to be attracted to areas of negative charge. Okay? So opposites attract in terms of electrical gradients. So ions in solution are influenced by both a concentration gradient, also sometimes referred to as a chemical gradient. So concentration gradient and chemical gradient are synonymous. And they also are influenced by electrical gradients. Okay? Now, sometimes those two gradients are pointed in the same direction. Sometimes an ion, its chemical or concentration gradient is pointed in the same direction as their electrical gradient. Then there's no issues, right? There's one priority. But sometimes ions, their chemical gradient is actually pointed in the opposite direction of their electrical gradient, and that's when things get a little bit more complex. So for all of these ions, the natural drive is to reach a state of equilibrium, meaning that there's no net driving force. Okay, there's no driving force for movement. And as I talked about in class, equilibrium, your cells are not actually in equilibrium because a state of equilibrium actually means the cells are usually dead. So while these ions are striving for equilibrium, they're not necessarily ever going to be able to get there until the cell dies. But these ions are striving for a state of equilibrium where there's no more net movement, or there's no driving force for net movement. So this equilibrium, when you're talking about an ion that has both a concentration gradient and an electrical gradient, for this equilibrium to happen, basically the chemical gradient and the electrical gradients have to be equal in size but pointed in opposite directions. Okay? That's an essential concept, that in order for an ion to reach a state of equilibrium, its chemical gradient and electrical gradients must be equal in size but pointing in opposite directions. So then finally the ion has no more net driving force for movement. Okay. So this point at which the ion is in equilibrium is described as the equilibrium potential. Okay? And it's going to be some voltage where an ion's electrical gradient completely balances out its chemical gradient. Okay? Now, the equilibrium potential is going to be dependent on the valence of the ion, and valence simply means the magnitude of the charge. So for sodium, the valence is +1, right? For calcium, the valence is +2. For chloride, the valence is -1. So it's the actual number of charge. And also, it's going to be dependent on the extent of the concentration gradient, or the difference in the ion concentration across the membrane. So calculating the equilibrium potential, which you will not have to do for me, calculating the equilibrium potential, which is expressed as E sub x, is determined by a form of what's called the Nernst equation. And the reason why I'm showing you this equation is I just wanted to point out that this part of the equation, right, xi over xo, really stands for the concentration of the ion in the inside of the cell compared to the concentration of the ion outside of the cell. So this represents that concentration gradient. And then if we look at this part of the equation, V sub x, that stands for the valence. Okay? And then these other factors in the equation are, there's two constants, okay? And there's temperature. So the major factors that contribute to equilibrium potential is the concentration gradient and the valence of the electron. So let's consider the equilibrium potential for our two key ions, for sodium and potassium. So sodium and potassium are both have a valence of 1, and they have a similar distribution of concentration, just in opposite directions, right? So sodium's greater outside by a magnitude of 142 versus 10 milliequivalents per liter, and potassium has a greater concentration inside at a magnitude of 140 versus 4 milliequivalents per liter. So we've got the plasma membrane, we've got the inside of the cell on the right, we've got the outside of the cell on the left. Now let's think about let's first think about potassium. So potassium, we've got lots and lots of amino acids and protein inside the cell, which means that the cell is starting out negative because of that. All right. So for potassium is a positively charged ion, and it's sitting in a negatively charged environment. Now, the concentration gradient of potassium is pointing out of the cell, right? It's got a greater concentration inside than out. So the concentration gradient is pointing out of the cell. The electrical gradient, however, for potassium is positively charged. The electrical gradient is actually pointing inside of the cell. Okay, that's the electrical gradient. Potassium is a positively charged ion. The inside of the cell is negative. So its electrical gradient would actually prefer it to stay inside the cell. So these two motivations for the ion are actually in conflict with one another. So for potassium to get to equilibrium, the inside of the cell has to have a voltage that creates a balancing out of these two gradients. Okay? And the equilibrium potential for potassium happens to be 90 millivolts. That means that the inside of the cell, when it gets to 90 millivolts, okay, when the cell gets to 90 millivolts, the electrical gradient is large enough to equal the concentration gradient, but they're pointed in opposite directions. So when the cell is at 90 millivolts, potassium no longer has a driving force for movement. Okay. Sodium is very different. Okay, sodium, the concentration gradient for sodium is pointed into the cell. There's more sodium outside than in. Okay. But let's look at the electrical gradient. It's negative inside the cell, and sodium is positive. So sodium's electric gradient is also pointed inside the cell. Okay. Now, that means that sodium has an enormous motivation to get inside the cell. Now let's say we let it flow inside the cell. Let's say that we allow sodium to freely cross the membrane. It's going to cross the membrane happily. It's going to cross very, very quickly and explosively even. So sodium enters the cell and it carries its positive charge with it. So for every sodium ion that moves in, the inside of the cell becomes slightly more positive. Now, eventually, enough sodium will enter the cell for the cell to go from whatever negative charge it started off, okay, to 0. Okay, so at some point, it's going to get to a negative charge of 0. And then more sodium is going to enter, and eventually the membrane, the potential inside the cell is going to start to become positive because now you have so much sodium inside the cell. And it's not until the inside of the cell reaches positive 60, okay, when the cell reaches positive 60 because of all of the sodium movement, when it reaches positive 60, now the direction of this electrical gradient is not only switched, but it's also now equaling the concentration gradient. Okay? So the equilibrium potential for potassium is positive 60. When the cell is positive 60, that represents the point at which the electrical gradient for sodium is equal in size but opposite in direction to its concentration gradient. And there's no more net driving force from movement. Okay. Now, so we know that sodium wants the cell to be at positive 60 because that's when it's at rest. Potassium wants the cell to be minus 90 because that's when it's at rest. The real resting potential of the average cell is minus 70. Okay? The real resting potential is minus 70. So the resting potential of a cell isn't satisfying either ion. Okay? It's not equaling the point at which potassium is at rest, and it's not equaling the point at which sodium is at rest. It's in between. So what does this really mean, that it's at minus 70? Because resting membrane potential is determined really by the composition of the ions. So resting membrane potential is really dependent on the ions present and their individual equilibrium potentials, but it's also dependent on the relative permeabilities of the membrane to each ion. Okay? So if we go back to this slide, what this means is potassium wants the cell to be minus 90, sodium wants the cell to be minus 60, but whichever ion the membrane is most permeable to at rest will be able to pull the membrane potential closer to that ion's equilibrium potential. And since the resting membrane potential is minus 70, that means that if this were a game of tug of war, potassium's pulling to minus 90, sodium is pulling to minus 60. Potassium is appearing to have the upper hand on this tug of war because minus 70 is closer to minus 90 than it is to positive 60. So it means that the cell, the membrane at rest, is more permeable, passively permeable to potassium than it is to sodium. Okay? And that's absolutely true. So the membrane potential of a cell is determined by the ions present and their individual equilibrium potentials, and it's also determined by the relative permeabilities of the membrane to each ion. Okay? And since the cell at rest is more permeable to potassium, it's the resting membrane potential is closer to potassium's membrane equilibrium potential. Okay? Now, this means, this means when we say that the cell is more permeable to potassium at rest, it really actually means that there are more passive leak potassium channels at the membrane than there are passive leak channels for sodium. And the average cell, in fact, has very few passive sodium channels, but has a greater density of passive potassium channels. Okay? So potassium has a little more opportunity to cross the membrane and go and try to get closer to its equilibrium potential, while sodium really has very little to no opportunity to freely cross the membrane and pull the cell closer to its equilibrium potential. Okay. Now, we started off talking about excitable cells in terms of muscle cells and neuronal cells. Now, an excitable cell is a cell that experiences large fluctuations in membrane potential. So if a cell's membrane potential is sitting here at -70, a non-excitable cell, any other cell in our body, we have very little fluctuation in membrane potential. So the membrane potential really doesn't change all that much compared to resting. However, with excitable cells, you have large fluctuations in membrane potential that actually create that electrical impulse, that action potential. So right now we're going to build towards understanding what goes on at the plasma membrane in terms of sodium and potassium during an action potential. But we're going to define a few terms. So we're starting at resting membrane potential of -70. If the membrane potential becomes more positive, okay, if it becomes more positive, we call that a depolarization. Okay? So remember, the outside of the cell is positive, and the inside of the cell is negative, which means that this membrane is polarized. Okay? So if the membrane potential were getting closer to a positive number, then it's depolarizing. It's becoming less polarized. Okay? If the cell goes from a depolarized state back to resting, we call that a repolarization. And if the cell goes, if the membrane potential moves from resting to a more negative voltage, we call that a hyperpolarization. It's becoming even more polarized. Okay? So depolarization, the number is becoming more positive. Repolarization is when it comes back down to resting. And hyperpolarization when it becomes even more negative. So the action potential that happens in muscle cells and neuronal cells, this action potential is a very explosive, large fluctuation in membrane potential. And this is what it looks like. Action potentials are described as all or none events, meaning that they have the same characteristic shape and component to it, And as long as you reach some particular threshold of membrane potential, you are going to fire an action potential. And all or none also means that there's no small action potentials and there's no big action potentials. There's just a single prototypic action potential. Okay? So different components of the action potential. So we are starting off at our resting value of minus 70, and something is happening. Some trigger event is happening that's causing the cell to depolarize. And then that depolarization reaches some critical threshold. Okay? And in this slide, it's being drawn as minus 50. So some critical threshold. At this threshold, all of a sudden, the action potential is triggered. And the first thing we see is a very rapid depolarization, a very rapid and extreme depolarization. So the membrane potential rises, okay, and it hits a peak of about 30 millivolts. Okay, and this is just an average um, for cells, reaches a peak of about 30 millivolts. And then it takes a very sharp turn, and all of a sudden it starts repolarizing, becoming more negative, right? And in fact, so it repolarizes, and in fact, it doesn't even stop at resting. It has a hyperpolarization phase. It becomes even more negative than compared to resting. And then eventually it gets back to resting. Okay? So the parts of an action potential, we've got our initial depolarization. Something's triggering an initial depolarization. Number two, we hit threshold and we have the rapid rising phase, the rapid depolarization. And we reach a peak and we hit the third part where we have a rapid falling phase or a rapid repolarization. And then the fourth phase is the hyperpolarization. And then finally, the fifth phase is going back to resting. Okay? Now notice two things. Notice that up here we have this blue line that's representing the sodium equilibrium potential. And down here in the light blue line, we have the potassium equilibrium potential. So the action potential has, in that rising phase, it's getting closer to the sodium equilibrium potential. And in the falling phase, it's getting closer to the potassium equilibrium potential. Okay? And what we'll see in just a moment is this rising phase is actually being driven by the movement of sodium. Okay? It's being driven by the movement of sodium into the cell. And this falling phase is being driven by the movement of potassium out of the cell. So let's look at what that looks like. So if we start off at that first initial point, we're at resting membrane potential. Nothing's happened yet. Okay? And if we look at a cartoon of the plasma membrane, what we see is ICF that has a net negative charge, right? And it's a net negative charge of minus 70 millivolts. And we have ECF that has a net positive charge. And then what we see here are two ion channels at the plasma membrane. Now, we've got an ion channel, potassium ion channel, and a sodium ion channel. Now, both of these ion channels are closed because these ion channels are what we call gated channels. And in fact, what they are gated by what we call voltage gated, which means that these ion channels are not going to open until the membrane potential gets to a particular voltage. All right. So first step, we get a triggering event. And the triggering event depolarizes the cell to threshold. So this minus 50 threshold, the reason why it's so special, the reason why it is the threshold, is because it happens to be the average voltage that opens up these voltage-gated sodium channels. Okay? So this activation gate on the sodium channel opens. And that's why the very next phase is the explosive entry of sodium into the cell, which causes a depolarization. Okay? So sodium rushes into the cell as soon as the activation gate opens, and the cell depolarizes. And as more sodium come in, the cell gets more and more positive. Now, this little ball and chain part of the channel is called the inactivation gate. So the way this protein works, this channel works, is when the activation gate opens, there is a particular amount of time that it takes for this inactivation gate to shut the hole. Okay? It's just a few milliseconds, but it's enough to allow a flood of sodium into the cell. And then that inactivation gate swings closed. So instead of sodium entering the cell and taking it all the way to positive 60, right, up here, right, it doesn't get a chance to get all the way to positive 60 because the gate shuts. So it can only get up to about positive 30. So around the time when sodium stops flooding in the cell, reaching that close to that peak, that positive 30 or so, that also happens to be the average voltage that opens the potassium gates, the voltage-gated potassium channels. And now the inside of the cell is very positive. Potassium is a positive ion, and its concentration gradient is pointing outside the cell. So at this point, potassium actually has a huge motivation, both electrical gradient and concentration gradient, to get out of the cell. And that's exactly what it does. So potassium flows out, and what happens is it takes its positive charge with it, and it starts to cause membrane potential to go down. Okay. Now, eventually, membrane potential is going to come down, come down, come down, and it's going to get close to resting membrane potential. Now, the potassium gates are a little slow, much more slow compared to sodium gates in closing. So what that means is that sort of sluggishness in shutting the voltage-gated potassium channel means that a little more potassium leaks out of the cell than is necessary to bring the cell back to resting. Okay? And that leaking of extra potassium out of the cell is what's responsible for the hyperpolarization phase of the action potential. Okay? But eventually the cell comes back to resting, okay? And the potassium gates are all shut, and the sodium gates are all shut. And this hyperpolarization actually serves a purpose. If you notice over here, when the, the action potential was at its peak, you notice that the sodium gate was in this configuration where its activation gate was open and its inactivation gate was closed. Now, that hyperpolarization ensures that all of the sodium gates are capable of resetting, which means that that inactivation gate gets out of the way and the activation gate closes. Okay? So that hyperpolarization phase ensures that the sodium gates go from this orientation, where the inactivation gate is in the way, to this orientation, where the activation gate has now closed the channel.